Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. I think we're gonna start. It's probably people are lagging after lunch, but we need to keep the show moving forward so everybody has time to talk. So welcome. This is our Digital Humanities track. We have 4 speakers today. Really exciting. My name's Donald Brinkman. I'm a program manager for Microsoft Research, and I manage, among other things, our brand new Digital Humanities program. So this is that's why it's so exciting for me, is that this is kind of the beginning of what we hope is a really, really rich and exciting exploration of a lot of really hard problems. Because some people might say that Digital Humanities doesn't have the data problems of other areas of the sciences, but when you really start examining it, you realize that it does. There's a tremendous amount of data out there. And moreover, it's data that is largely unorganized, or even worse, sometimes is extremely hard to organize. And I think that our first talk and I want to...
MC is fine. Really.
Yes, MC schraefel is going to give a talk on musicology, and I suspect she's going to be talking about encountering exactly those kinds of problems and her attempts to overcome them to create a general solution for so. Without further ado.
Okay, is this mic okay for you? Yeah? All right. Gentlemen at the back, would you care to move forward to feel a little closer? Because there's 8 of us here in this rather large room. And I feel that this is an opportunity to get to know each other so much better. Though this podium does feel rather like being at church. Okay, cool. Thank you very much. And since you're all here and came back from lunch, I'd like to offer you what I can only call a geek gift before we begin, because if we've just had lunch, right now our bodies are telling us to relax and to want to go to sleep and not move into our peripheral nervous system at all, and that's not great for our brains. But I won't ask you to right now stand up and do some good things that would help your peripheral nervous system, because I'm digesting too, and it would just be ugly if we did. No, okay, so here's a little gift for when you can't get at coffee. It'll just take a second, and really you'll be able to have it. So if I may ask you all to rise for just a moment, then I'll give you an antidote in a second too. This is, but I promise I will not ask you to sing. I promise, no singing. This is really simple. Here's a fun fact. The joints in our feet take up 24% of all the joints in our body, which means that they are wired with more nervous receptors than just about anywhere else in our bodies. So if you actually want to wake yourself up ever, which you might not want to do now, but I'm asking you to for this talk, is really, really simple. If you actually come up on your heels by about 1 inch, ½ inch, whatever's comfortable, and go down and do that a few times so you're hitting your heels hard on the bounce. Not only do you start oxygenating because you're happy and doing something kind of weird, but this is actually sending a huge amount of signals to your brain to say that your body is moving, and therefore it's actually needing, you can stop. It's actually needing to do something. And I promise you, by the end of this talk, I will give you the antidote if you're ever feeling really awake and alert and you need to relax, or stressed and you need to calm down. But that comes after the talk, because I don't want you to relax before this talk, okay? So if I forget, remind me. Well, before the next talk, you can bounce again. So we'll just have a hormonal roller coaster ride today. Okay, that's nothing to do with this project. However, it's a great thing to have. Again, I was just at a conference where we didn't have coffee at the break, and we were all going a little snaky, and this really helped. Okay, so MusicSpace, what this project has been about was really to start with researchers and to ask what kinds of problems they had that actually having better access to metadata, once we figured out what metadata meant, would do for them. And so we were looking at some intractable problems, and I'll talk about what that means in a sec. So my hope from this talk is that you will get a sense not just of this particular project, but that you might see opportunities if you know any other folks in the humanities working with information who might have similar problems, or that you yourself with data sets might be able to say, these are the kinds of problems that I think I would like to be able to explore. This tool can help, because what I'm going to be talking about is a tool that we've really tested now a lot, is very functional, and does solve the problems that we're addressing, or at least make them more tractable. And so that you might want to do the same. So just to set a bit of a context, because this work started in eScience, and we all know that there's lots of data in science, and one of the challenges is how do you actually let humans get access to this information so that it can be explored? Discovery is an important part there too. Once you find a source, you want to take a look at it, see if it might be important to what you're looking at, and then start to query it and then do some representations on this. When we looked with musicology as a specific example in the humanities of how we could translate eScience work over to the humanities, was a question that was very similar about how we might look at attributes of interest in a data space to musicologists and be able to bring together those attributes no matter what data source they were in for fast querying of what we came to call, and this was the musicologist's term for it, intractable queries. Now, when we proposed the notion of intractable queries to the funding bodies, one of the pushbacks that we got from reviewers was, how do you mean intractable? How could you possibly solve intractable quandaries? Well, the thing is that intractable doesn't mean insolvable. It doesn't mean NP complete. It simply means that it's too difficult. You could solve it if you had the mechanism to do it, but it's either too time consuming or you can't get the resources even if you know they exist. So that's the kind of problems we were looking at. And these are sample questions that musicologists had that would say, these are too difficult. We want to solve these kinds of problems. For instance, how do you find out which singer sang the role of Malatesta in Don Pasquale? Now, that might not be something that will cure cancer if you find out the answer to that, but it is something that is of interest for the musicology set who wants to look at and understand better how a particular cultural practice arose around a particular role and why this is a recurrent theme. And by intractable, again, a musicologist would tell you that to get at this information, you'd have to look through a lot of sources manually in a variety of places, and even at that point, you wouldn't necessarily know that you had completed your mission. Was this exhaustive? And again, for instance, our fellow in the 20th century was looking at what are all types of electronic instrument used by John Cage, in particular decade of work. So if you get a raw index, for instance, they don't exist. There isn't an index that maps instrument to composition. That's one thing. And if it's another thing, being able to see from that index what period a work was created on, et cetera, you get the sense that if the lists existed, you could do these questions. So we're trying to say, can we pull together data sources to enable these kinds of questions to be explored, which, again, we wouldn't actually call these days, they don't look like deep, hard problems. But again, the musicologists assured us that if they could answer these kinds of questions, they could do new and novel types of research papers that they've had to literally set aside because getting at the information in the normal sources was difficult. Let me go back to this slide. I've got 6 different data sources at the bottom. These are either commercial data sources or open data sources that have been funded by research councils. The British Library and Grove, Naxos are very commercial. RISM, Cecilia, and Copac are less so, but they are well curated, and they all have different types of data sets. They all live either partially in some kind of warped database or where original sources that existed in text have now somehow been squished into a database, so not very good field excavation from that data. And they all represent different things. The British Library, for instance, has a sound archive where you can get at samples of recordings or whole recordings. Naxos has listings of performances and recordings. Grove Music has works lists, so what composers have actually done. Copac, RISM rather relates to things like articles that are about things. So you can see how if you could pull all these things together, you could ask some interesting questions like the ones we've suggested. And also, what we wanted to be able to support is that by looking at context, or looking for, rather, the answer to your question, would it be possible to expose what else might be happening around that particular query of interest? And I'll come back to that in a sec. for what we might call serendipitous discovery. I mean, it's pretty difficult to engineer for serendipity when serendipity is predicated on the fact that you don't know what you're looking for when you fall over it, and you can make something of it. But we wanted to, again, facilitate that sort of, oh, I didn't know that, or that's the first time I've seen that. That could be interesting. Can I explore that? The problem, again, this is probably very familiar territory, is that as we look for the same thing, in this case we're just looking for opera, it looks very different across a variety of data sets. So there's, again, another reason to want to harmonize these. And one other thing that we found out that was really dissatisfying for musicologists, and as we all probably know has a tremendous effect, is that even using these single dimension data sets, if you will, or single focus data sets, they're slow. That was a surprise, but this was apparently extremely dissatisfying for the folks using the systems. Our approach, real simple. How about we take all those sources metadata, blend them up, put a UI on top of it for exploring the information, and then we make it robust enough so that we can test it in the field for 6 months to see if it actually facilitates research. This was one of the biggest parts of this project, was number 3, which was to be able to actually have a system that worked well enough that real researchers could use it to actually have enough time to see if this would contribute to their doing real research. That was kind of a risky strategy, because what happened if the project failed and nobody could do the research? And also we were a little bit hamstrung by the agreements that we had with the data set providers, because commercial databases tend to see their metadata as something they want to sell. And so we had license agreements for them for sections of their database, so that we said, look, we just want to look at these 3 areas in musicology. Could we have the data just for that? And probably it would have been easier for everybody if they had just given us their database dumps rather than trying to do segments. But segments meant that we actually could get the data from them, and that their masters wouldn't feel too aggrieved that we were doing this research thing with their data, and promised not to let everybody on the planet see their precious metadata. It's an education process, really, to get that if they expose their metadata, and we'll come back to this, they actually have a greater chance of uptake of their actual paid assets if they let us get at their data. So the first challenge, again, of integrating multiple sources is the same old story that all of us are familiar with, I'm quite sure, of alignment, some sort of referential ontology or thesaurus, the completeness of the data, and actually something that turned out to be quite a surprise was the granularity of the metadata needed some help too. And then, of course, on the front end, we needed something that would solve some of the issues about being able to explore the information. It's not enough just to show it to people. People have to be able to interact with it quickly. As quickly as they think of a query, they have to be able to explore that. The other thing is that when we got data sources, it's all in every format under the sun. And, you know, again, that's just a pain in the neck to deal with. It's not an intractable problem for us. It's just an irritating one. And so one of the, just as a takeaway from this, is that we translated everything into RDF because of the flexibility with RDF as a data exchange format. We've tried everything else, and we found, again, that for what we're doing, especially on the UI end, that it's easier to augment data sets if they're saved in RDF. So that's just a technical takeaway. And the kinds of things that we wanted to support is, for instance, if we're looking at a model, a very simple model like this of relationships to information, such as a composer who might have a name, publisher, year, and title, we wanted to get a little richer in terms of the relationships that we could enable people to explore effortlessly. So this was how the multiple data sets might be integrated. I won't go into this graph. But what that meant is that we actually got into, when we were testing this out at various stages with the musicologists, of creating a finer granularity for the data than was actually in the data sets. We didn't anticipate needing to do this. But this is an interesting effort of triage, and I would suggest that anybody who goes into this kind of domain space with humanists is that they do a litmus test, if you will, of what the schemas are coming out of the data sources to validate with the practitioners if those fields are sufficiently fine-grained for them to ask the kind of questions that they want. And if you have the data and they say, well, actually, really, for instance, we would have date from a data source like Grove. And what does that mean? Does that mean the date the thing was performed? Does it mean the date it was composed? Does it mean the date it was published? Other data sets might have that data, so we had to create some new fields. This became, as I say, something we didn't anticipate necessarily needing to have to do. And this is one of the value adds, though, that our commercial partners get back from this, is they get input from real users to say, we want this data, and it becomes a service opportunity, not that anybody's paid us for it yet, to actually enhance their data assets by creating this granularity inside of the data set. So now I'm going to show a bit of a screencast of what this actually looks like when it's in action. And the challenge is that we're looking for works by John Cage, which performers have recorded a particular work, and what else by Cage have they recorded. So this is, if I can stop this for a sec, just to explain what you're looking at. This is, again, what would be an intractable query, but also really basic. You know, you might want to ask the question, so what recordings of Cage do we have access to in this set? Who's performed it? And have they done anything else by Cage? So you can see the kind of associations that one might naturally have while they're exploring this question. This is not easy to do with Google. It's not easy to do in a single data set. But it's such, again, this is a basic query. We need tools to support it. And this is what we designed this prototype around to support. And so as what you're seeing here is a faceted view of a browser in which we have a bunch of attributes. What I showed you on the previous screen with person and date and so on was that we have additional attributes that you'll see in a moment. At any point, the user can, and you'll see this in the demo, a person can pull in one of those facets to anywhere in what we call in this set of facets, we call that a slice. So the attributes within a facet slice can be reorganized to suit the formation of the query. And once that's done, the results can be shown and shared. This is one of the things, again, that the musicologist asked us back for that was so simple we'd never have done it, right? That's too easy, which was to be able to share the output of the query with their colleagues. And let me just walk through this with you now that we've got a sort of overview. So here the person has put up the query to look for John Cage information. They are now reordering the slice, that was the button they just hit, to be able to see just that information that they're looking at. So you saw a bunch of columns disappear. They're swapping Composer around to rearrange the query to get at the works by that organization. They're going to click on one and pull up the performer so that they can then see who the performer of that particular piece is, I believe. So they're looking at all the information that they get back. All of these being recordings are from the British Library Sound Archive. They're now pulling in performer. The query rearranges itself. Now you've got the list of performers and pulling in where it was performed. That's cool. I didn't know we had that in the data. I learn something new every day, but because this field wasn't part of the original data set. And so they've decided they want to share this or save this query for themselves. So they've got just a simple text output. This is as simple as they wanted it to be, something that they could mail to themselves and also have a URI for that state of that collection. They're now looking at performers. By swapping around the column, they now get to see anything else by Cage that this particular performer has done. And boom, they've got it saved, and they're done. Previously intractable now looks absolutely trivial, which is the state of play that you want to get to. I'm so happy I could spit. Okay, so this is the next thing that we were able to do in this project that, again, was a huge win, really exciting, very risky, to get the prototype to be robust enough, because those of you who've been working in software know that having to pull together data sources with a fast UI is kind of non-trivial if you want to give it to real people for real use. So we were able to do this 3-month longitudinal study. We had, amazingly, 67 participants, which, for those who are familiar with the Chi literature, you can usually get 8 people in a room for an hour. So we're pretty happy about this. And the other thing is that this is a really narrow field. We had only 3 areas that we were looking at. Opera buffa. I learned a lot about music doing this project. So opera buffa is one, Schubert songs is another, and 20th century electronic recordings was another. And to find out that in the UK alone we had 67 people that knew anything about that was pretty cool. And that 41 people were actually using the tools over this period. I mean, again, It's not Google, right? Google is the hammer for which everything else is a nail. This is a slightly more refined tool, but the fact that we had an average among these people of 12 sessions, where each session was lasting just over 15 minutes, and that there were 31 exchanges within a session of that long, is pretty cool. Because that means that they're using it repeatedly over the period. The things that they commented on, and we'll go over a little bit, was the fact that it was fast. They started using this tool even if they wanted to search one archive because it was faster and a better UI experience for them than using the local tool. So they'd go here instead of the British Library Sound Archive. So there was a convenience of one access point as well, and of course the novelty of the questions that they could ask. And of course the proof is kind of in the pudding, but solving the intractable questions is, for instance, this person puts it very well, we know how to collect evidence to support the fact that we did what we said we did. So when we were talking to people, this is the kind of reply that we got, is that, I won't read it to you except for the last bit on the page, is that doing this kind of query, you'd need an index of characters that doesn't exist, you'd have to manually collate the information, you would also have to know what you were looking for before starting out. This is one of the cool things about this tool, is that you can, because you can see the domain space in the UI with those columns, with those attributes, and start to put together a space and rearrange it to focus on a point of interest for you, that enables you to start to see the context of the world and ask, oh, I wonder what would happen if I did this. Is there a relationship here? Did anybody do that? And it costs very little, and you see the results right away. And so this enables this kind of exploration. We were talking about this last night, exploration as opposed to browsing. Browsing is, we would say, where you can just kind of hop along following a link, whereas exploration means, we're saying, you have a sense of a map of the territory. You can kind of see what the territory is, and you're making more specific path-finding movements through that space. Another kind of example here, this is the best part, is that, again, we're able to have it in the field long enough for when people were doing their work as a natural part of their process, they were able to go through searching with our approach very quickly and tell us that this relates, what they were able to do relates to my current research project. So these weren't faux queries where we were saying to them, could you do a query to answer the question blah, which we could have done as a test data set and actually did initially just to make sure that the UI was working. We generated queries with other musicologists to say, oh, could we get some kinds of questions that this UI could answer, and then we'll just see how long it takes musicologists to get up to speed using it with very little tutorials on how to actually use it. But that we would get this from sort of research in the wild was awesome. And again, similarly here, again, the type of associative exploration here that folks could carry out, so that we wanted to find out about gondola songs by other composers. So again, this is looking at the association of this trope in this particular space, that the facts discovered here are being used in a forthcoming article. And one of my favorites, and I will read this one to you, is that I used the preset recordings column layout to look for information about Clifford Curzon and Nadia Boulanger. I discovered an unpublicized pre-war off-radio recording of the two playing a two-piano recital. That in itself was a find that was important, and it was just effectively, oh, this is what came out of browsing to look at this, to see what's available in a nice compact way. I went on to explore Curzon's subsequent recording career. So now looking forward from where the actual query was, something you can't easily do. Again, if you knew what you're looking for, you asked Google for it, and somebody had the result to say, this is this thing that these two played together, that's it, you're gone. This way, though, you can easily move forward through the space. And what I was particularly interested to see was that he was already recording Schubert in 1941, very early in his recording career. This research will contribute to my current book project. So again, just by being able to explore the frickin' context of that space easily, new and novel research is becoming accessible. So quick outcomes from this work related to this is that the MSpace framework that facilitates this UI is available in open source. Not only that, but because we know that we want to add more data sources or make it easy for people to add data sources or create their own MSpace for music, archaeology, history, English, whatever, we've created a facet picker that, again, when sources come out of RDF into a triple store related, it's called a Sparkle endpoint. Right now, the data picker We'll work with Sparkle endpoints to enable you to decide what attributes in an RDF source you'd like to make as facets and what you'd like to make as a primary source. There's a wee link under there at blog.mspace.fm which shows a demo of this tool, and you can download it now too. And the other kind of cool, exciting thing that also there's a screencast for is this notion of a pivot maker. So for instance, if you've got two distinct data sets, for instance, you've got musicology here and you've got architecture over here, and you think that there's a map on Baroque between the two because you want to explore what the relationships might be there, you can have M spaces intersect. Oh, it's wicked. Because you can start to see what the relationships are, not just within the domain, but around the domain. And in fact, that's come out as really important. So what MusicSpace gave us was a fast way to explore information on multiple sources in a way that let people not only just look for stuff, but then share the URI from the state of whatever the interface was in, so that if they said, this is the slice, this is the path I used to get to this information, they can share the URI on that. There's a bunch of tools, as I just showed you, to help people make more of these easily. Co-reference, we've heard about that a lot in the past 2 days, is still ugly. We've even got a tool now that helps with that. Our approach is to look at, for musicology, again, this is part of a new project called MusicNet, where we're trying to mint canonical URIs for these kinds of data sources. So what you're looking at here is, for instance, all the data sets that we have munged together, and all, in this case, ungrouped S's are on the left and grouped S's are on the right, which means that if you've got a shed load of Schuberts, oh, that's alliteration. Okay, if you've got a shed load of Schuberts, as we do on the left, as you'll see, you can now just quickly drag those Schuberts into a group that says, this is Schubert, and use that one label, or any label you want, will refer to the correct Schubert. And the cool thing about this wee tool is that it will, as you see original sources beside those columns, is that if you pick on one, so for instance, here's a Franz Schubert, and you want to make sure that's still the Schubert you're talking about, because as you see in this list, sort of there are other F Schuberts as well. Amazing. You can hit the original source, see that yes, indeed, based on other information, this is the Schubert that you're talking about, and then just drag that Schubert with confidence into the other list, and you've now got them grouped and ready to be associated with that single URI. So this is a community-based tool. We haven't developed a policy language around this to say this is how these paths will be validated to make sure that not everybody is calling everybody with an S Schubert. And so on, but that's a problem for another day. The main thing is that we can actually give it to people that we trust who are interested in wasting some of their cycles to contribute to the community. And again, the discussion about how does the community get validated for doing this work, this is something that would be worthwhile. If somebody's taking time out of their day to actually validate and clean up data sources, they should be supported for that. So the few takeaways from this is that the growth of this has been able to start with real problems. This project was founded on, we want to solve these 3 questions that musicologists have about these 3 domains, and can we do it for them, and then have people also related to these domains solve questions for themselves too. Google is really right. The UI and the experience has to be fast, or people will walk away from it. You could have the best UI on the planet, and we think ours was pretty good, but when it was slow, it's like, wow, you've got a great UI here, call me when it works, okay? And another part of it that was really, really, really critical, and I encourage folks to put time into their funding proposals for this, is to actually evaluate it in the field. Test yourselves to say that which means you have to find time to make it robust enough to get into the field, and that's hard. And the 4th takeaway is that we had experts in musicology as part of the team. They weren't people that we consulted with. They were people who were team members. They were invested in the project, and that was invaluable. We've done this now at least 3 times where we've had mixed expertise teams locally. My goodness, I know that Dave is going to be able to speak to many of these things too. Future work is that we have to do more and link more. Musicologists were already starting to ask us, just to focus on Schubert here, that's the Schubert selection in the middle, is to be able to, can we bring in other data? Can we start to pivot? Can we start to show the associations, not just in music, but what else was going on at this period in the early 19th century. I mean, it was incredible. Georgian architecture was happening. We had the Austro-Hungarian Empire is still doing weirdnesses. We've got Roure, who is starting to say that you have to think about, or Augustus Comte is starting to say we have to think about statistics in the social sciences. You've got the Bronte sisters writing. You've got Madame Marie Curie talking about radiology. All of these things are going on at the same time Schubert is writing lullabies. Does that inform the sound of the music of that period? Does it resonate or contradict the architecture that's going up around Europe at that period? Is it in a sense affected by the politics of the climate? Do they reinforce each other? This is all in the data, and lots of it can be coming out of the metadata. So again, I think these are some of the places where at least we want to expand further, and where we think it's all in the link, and we have to be better at exposing, to integrate these kinds of queries, not just to ask questions even in the eScience space about the gene, which is hard enough, but to the context of the discovery. Just for your information, these are some of the URLs. The easiest one is mspace.fm, from which all of this stuff here flows. But again, most of the demos that are up there and the tools you can download for yourself, and in particular, acknowledgements for this work do go to Tony Hay, for actually saying at one point, way years ago when I started to push on usability in eScience, that okay, I get it, that usability might be important when some of the tools were kind of falling over for not being in that. And in particular, Dave Roure, Jeremy Frey, and Carol Goebel, who were there leading the charge and invited me to the party to start working in this space within eScience and encouraging this work. So I can't thank them enough. And of course, there are people who fronted some money to make this happen as well. So if you have any questions and we have any time, I'd be happy to take them.
Thank you.
You're welcome.
So we're a little touched for time. We have time for a couple questions, but I'd like to ask Tenzing to come up and
Oh, sure.
get set up. And well, keep the mic for the moment.
Oh, okay.
So,
got a quick one, MC. There's quite a lot of, it seems quite trendy to have sort of graphical graph-based browsers for looking at relationships, and your UI is purely, well, principally text-based in terms
Absolutely.
of, and so what are your views on sort of where you might use a graph-based UI versus a text-based one in terms of usability?
I can't tell you how happy I am you asked that question. If I might reiterate it a little bit, it's what's all the graph. I did a paper with David Karger at MIT a little while ago. I think it was called Big Frickin' Graphs Suck, and it was an ISWIC paper, a semantic web conference paper, and I think that we could safely say that visualization is a really important part of an explanation process, but it is not where the heart of the information is. Lists are really powerful. When I look at a graph, there's been research done to say that when you have a graph, supplement it with text. Explain what the hot spot is in that graph. And you don't even want to see the whole graph. Usually when you're presenting an entire graph, it's so that you can point at the middle dot, to say the middle dot is really important because of this context around it. We are visually oriented people. Vision is our highest sense system, true, but cognitively, explanation is really important. So exposing the textual metadata is more important for actually getting at facts of discovery. And then once you know what you want to show, being able then to put that onto a graph is a fabulous way of being able to then communicate the importance of what is important to you. Starting with a graph, I often find, is just starting with a pile of spaghetti and trying to make sense of the spaghetti. Whereas sometimes just getting a number back, how many edges connect on this graph? How about just a text response that says there are 6? Great. How many others are there? No one has greater than 2. This one has 6. Wow, I can do the stats on that in my head to say that's 3 times bigger. Whereas if you showed me the graph, it's like I'm going to be going, okay, this is kind of big over here. So I guess the fundamental question is, what do you want to communicate? And if you start with what you want to ask or what you want to communicate, you will find out where the graph makes sense. If you start with, I have this great graph software, and I want to make graphs, that might not be the best way to support communication, depending on what you want to do. So, say it all depends. He's standing.
We can, very quick.
Very
Just
quick.
we have to be.
I'll be really short.
How long did it take to do the team, or how long?
This whole project, starting with the fact that we actually had some of the framework here, in terms of all the relationships of working with all the partners in testing, 3 years. But now it's done, and it will only take you 3 hours to install the software.
Thank you, MC.
Pleasure. Here you go.
So next we have Tenzing Shah, who's, I'm sorry, you're from NCSA, from University of Chicago, who is going to talk to us about taking...
University of Illinois.
Oh, University of Illinois.
At Urbana-Champaign.
My apologies. I've met all of my speakers for the first time today, so he's going to talk to us about extracting geographical information from digitized maps.
So my talk is called Quantifying Historical Geographic Knowledge from Digital Maps. And I will explain that in just a second. But I'd like to mention that it's a project in conjunction with some people at the English department at my school. So I'll explain that too. Okay, some acknowledgments. The maps are from our library. Okay. So what are these people at the English department working on? They're working on taking historical maps. In particular, they're interested in a data set of British and French maps of the Great Lakes region from about 1650 to 1850. And the British and the French at that time were competing for dominance in the region. And what they want to know is who knew more about the region's geography and how did that relationship change over time? The Indians. Well, I would assume that both of them tried to get information from the Indians. Okay, and so we're trying to develop algorithms to help them do this. Okay, and above, and on the top there you see a British map from 1801. This is actually a cropped image of Lake Ontario from the map. And there you see another image of Lake Ontario from a French map from 1759 at the bottom. And we focused on Lake Ontario in this project. At least that's what we've mostly been doing. Not picked for any particular reason. It's just a starting point. And
It's a really big lake.
yes, but we're also moving to Lake Superior, which is much bigger, of course. Yes. Okay, but I'll get to that later. And so, as I said before, what they want to learn is who knew more about the region and how that changed over time. So, in particular, we're looking at who knew more about the shape and size of Lake Ontario and how did that change. And what we want to do all of this automatically using computers. So previously you could just look at them and subjectively try to guess who knew more. And obviously the top map looks better. But how can we quantify that? That's one of the big questions. And I will explain what measure we're using. Okay, so that's the image collection. And also, in order to quantify who knew more about the region, we need to have a standard for geographic knowledge. And obviously, those are contemporary maps, because we assume that right now we have a very good idea using satellite images of the size and shape of the lake. So we'll compare both sides to modern maps. And here is the approach. It's a diagram that's supposed to illustrate the algorithm. So On the top, you have a bunch of British maps of Lake Ontario. On the bottom, you have some French maps. And the measure that I chose to work on first was to compute the areas of these maps. And then you can compare those areas to the modern area, which is known. And I'm sorry, the area of Lake Ontario. And the lake area is known very well today. And I thought it would be interesting to see how computed versions of that area in historical maps compare to the known figure today. And so in order to calculate this area, what do we have to do? First, we have to know which pixels in the map belong to Lake Ontario. And that's a segmentation problem. So segmentation is the first step. And area is an absolute quantity. Therefore, we have to perform calibration on the maps. And the scale of the maps is not known beforehand in this case. So we have to know how many miles corresponds to how many pixels. And once we've done that, then we somehow analyze the shape. In this case, we compute the area. So add up all the pixels in the lake and multiply by the appropriate conversion factor. And so then we can compare French and British maps over time in terms of their beliefs about the lake area. Okay, so first I'm going to talk about the segmentation step. And what we do is we use region growing segmentation. So here's the original image, if you can see my mouse there. And in region growing, as some of you probably know, you drop a seed somewhere in the map, and then you grow a region from the seed location, hopefully filling the entire lake area. And this region growing algorithm depends on certain parameters. And the question is, how do we choose these parameters, since all of the images are different? And we can't just hard code parameters. So we need a way to choose them intelligently. And this is a binary image, is supposed to be the output, obviously. So how do we choose the parameters? The way we do that is we have an example. And the example is a segmented version of the lake from a modern map. And so what you tell the algorithm is, I want to find a shape that looks like this, and choose the parameters accordingly. And the way we do that is we use the who moments, which have been used in optical character recognition previously. And we compute the who moments of the segmented object for a given set of parameters, and the who moments of the example, and then take the Euclidean distance. And this allows us to search over the space of all parameters and find the best one, or the best set according to this measure. Okay, so I'm going to show you a sequence of images, which will hopefully illustrate how this is supposed to work. And here's our example shape. And I'm going to illustrate it on a modern map. You could also apply it to modern maps, of course. And I think this is a good example because we have some annoying clutter. Many letters, some folds in the map, differences in brightness. And these exaggerated, I don't know exactly what they are. Some sort of man-made? Yes. Right. Yes, things that are not really there, or are much smaller than they're depicted to be. So given these, how can we accurately segment the map? Okay, so this is a first try at segmenting the map, which is very bad, of course, and the distance is listed up here. And now the algorithm continues its search. And what I'm going to print out is the sequence of minima that the algorithm finds. So this is the next one. And here's the global minimum that it found. Obviously, you have to define some discrete set of parameters that you want to search over. So it finds its global minimum. And here are the optimal parameters. There's something called a ball size and a threshold. in the region growing algorithm underlying this. Then there are still annoying holes, so we have to get rid of those because we're assuming that we have a simply connected object. So if there are any islands, we're ignoring those. So we put a seed outside of the image, and do region growing again. And this ball size parameter allows us to fill in the holes because it basically prevents the region growing from leaking into the gaps. And so this is the final result. Okay, so why did we choose who moments? Because they were created, in fact, mathematically to be invariant under similarity transformations. So that's obviously what we want in this case, because the lakes could have varying size. We don't know the scale or the resolution of the map image. And you may have some rotation. Okay, so these are obviously good properties, and we can evaluate the accuracy of the algorithm by manually segmenting the lake and then taking the difference between the two binary images and the energy in the difference image. So that's the accuracy measure. Okay, now for the calibration step. So if we want to compute any areas, we had better know how many miles are in 1 pixel. Otherwise, we'll just get an area in terms of pixels, not an area in terms of square miles, which is what we want. So how can we do this? And there are two approaches. One, which we started out using, which is manual calibration. So you pick 2 points on the map of known distance apart, and you compute the pixel distance between them, and then take the ratio, and you have your calibration, for example, the length of the Chesapeake Bay. You don't want to do this close to the Lake Ontario image because it would skew the results. Okay, but this is no good because it's manual. It was just a starting point. So what we're working on now is a way of doing this automatically using what's called a graduated neat line. And that's a dashed border. You can see this dashed line here. Border around the map. And it actually maps the characteristics of this border mapped to the scale of the entire map. So I'm going to explain this briefly now. So we look at this neat line, and what we're looking for is the number of dashes in the neat line between 2 intersections with latitude or longitude lines. So here's 1, here's 2. So you count the number of dashes between these 2. And according to the historians we worked with, due to cartographic practices, this should map directly to the scale. And so if we can find that number, then we can go to a lookup table and find the scale. Okay, so what do we need to do in order to do this? First, we need to find the dashed line itself. Obviously, the computer doesn't know where it is to begin with. So in order to do that, we need to find all the lines that have, in this case, a vertical orientation. And we need to classify them, which I think is an interesting problem, and I'll talk briefly about it. Then we need to find the distance between 2 intersections, find the length of a dash, and take the ratio of those 2 quantities, and we get our number. And then go to our lookup table. Okay, so I'd like to talk a little bit about classification, because I think that's quite interesting. Here we have a solid line. So we've already found the lines in this step, and we want to classify them. Okay. We'd like to classify them as solid or dashed. And the question is, how do we do that? It may seem very easy at first, but the problem is there could be noise and other factors, or very low contrast, which makes a dashed line seem like a solid line. So naive approaches, like taking the variance of the dashed line signal, don't work. Okay, first of all, what is this signal? We get it by summing perpendicular to the lines to create a one-dimensional signal, because that's really what we're dealing with here. So the dashed line should look like a square wave when we do that. And over here we get some noise, because ideally it would be uniform, but of course it's not quite. And how do we look at these two signals and tell which one is dashed and which one is solid? And what seems to work very well is taking the autocovariances of the signals. And the feature that I use is the energy in the first peak of the autocovariance function. So for the solid line, the energy in the first peak, what is that? Well, you find the 0 point over here, move over to the first 0 crossing, and that defines the first peak. And you take the area under that. For the dashed line, you find the 0 crossing and do the same thing. And you just get there. I can barely do it with a mouse because it's so close. So obviously, for most of the dashed lines, that we're going to get very low values for that feature. Then you compare it to the total energy of the signal so that it's scale invariant. Okay. And this works well for all the maps we've considered. It linearly separates the data. It's just a one-dimensional feature. Anyway, that's how we do classification. And so here are the results so far. I've been developing this continuously for the past few months, and right now we're at about 60% accuracy on our data set. So 60% of the time it comes very close to the right answer, and I'm hoping to improve that, obviously. But when it does come close, it does very well. But sometimes it does really badly, because you can have really bad things going on in the maps, like this funny fold here, and some rivers intersecting the neat line, which obviously distort our calculations. And often we have issues of contrast also. Okay. So now I'd like to talk about the area computation. The area computation itself is trivial, but I'm going to give you the results. As long as we have the binary segmented image and the calibration, we get the area. And then we plot it over time for French and British maps. So here it is for Lake Ontario. By the way, this data corresponds to automatic segmentation, but manual scale calibration. So we haven't integrated the automatic scale calibration yet, but we plan to do that. And so British maps are in red, French maps are in blue, and we plot them from 1650 to 1850. The green dotted line here represents the modern calculated area of the lake. And so, yeah, it's very early, they were very inaccurate, which makes sense. And then they became much more accurate later. And I was told by one of the historians I'm working with, another graduate student, that around 1760, technology for chronometers on ships improved dramatically. And so you can see at least a lot more precision than, if not overall accuracy, after 1760. The points get much more dense. So, and also, rather surprisingly, we don't see much difference between the French and the British maps in terms of accuracy, because the French have more error, but to be fair, the average creation date of the maps is earlier. Therefore, you would expect more error. So, but obviously, in order to have better conclusions, we need more data. And we're working on getting it. We'd like to have hundreds or thousands of maps instead of about 40, which we do now. Okay. So Lake Superior is something we've just done a few days ago. And this is just for manual segmentation. We haven't run it through the automatic segmentation yet. And it's just to see what would happen, basically. And I thought I would include this. And again, the green line is the modern area, about 31,000 square miles. And you can see that in this case, French maps, earlier French maps did demonstrate more accuracy than earlier British maps. Although, again, you could dispute that because we don't have much data. But it's a starting point at least. And historians, the historical view is that the French did know more about the region early on. Right. And that's incidentally, that's why the French maps tend to be earlier and the British maps tend to be later. Okay. So here's the conclusion down here written by the student I'm working with from the English department. But take it with a grain of salt because we want more data and we want to automate the process fully as well. Okay. So here's a summary of the work. And basically, the segmentation, we have about 65% accuracy. And for the scale detection, about 60% accuracy. And we're working on both of those numbers, trying to improve them. And so we've only dealt with Lake Ontario and Lake Superior so far, just starting with Lake Superior. And we obviously want to do more regions in the future and have much more data. And we're trying to acquire that data now. I guess that's all. I actually have more slides on the scale determination, but it gets kind of technical, so I thought I wouldn't include it unless people had specific questions. So, does anyone have questions? Yes.
Did you account for potential changes in geographic projections between British and French maps?
So yes, that is actually something that we need to do. I thought I had put it down here in the future work, but I see that I haven't. Yes, you're absolutely right about that. Our assumption now is that it doesn't matter too much because the object isn't that big. But so again, I mean, there are a lot of things that we have to do still, and you should take the results with a grain of salt. And it may not be. It also may be difficult to even determine what projections were used in the historical maps. And I don't really know if that's possible or not, or how well people can do it at this point. I would have to talk to the historians about that.
Hello. I was just wondering about the segmentation algorithms, because if you talk to people in image processing, they keep developing new, less accurate, and there is a huge discussion on segmentation algorithms for different purposes. So why did you choose this particular algorithm? Did you go through different segmentation algorithms and then set on this one, or was just some evaluation that it would be best suited for the kind of data that you have?
No, honestly, it's something that I picked because I thought it looked reasonable. And it was kind of an ad hoc decision, I'm afraid. And so that's why I say that we have to improve the segmentation algorithm and maybe even choose an entirely different approach, which is better suited. The Who moments are kind of old, but developed in the 60s, I think.
Thank you so much, and thank you. If you have more questions, talk to Tenzing afterwards. We're trying desperately to catch up here. with our timing. My next speaker is David Roure, who's recently from Southampton, University of Southampton, now at Oxford. He's going to also be talking about musicology.
Yes. Yes, the obvious conclusion of which is that you and I should have a discussion. Right. The title of the paper is Data-Intensive Research in Computation and Musicology. And my co-authors are Stephen Downey at Urbana-Champaign, University of Illinois, and Itch at McGill. But the title of the project, which we'll come on to in a second, is SALAMI, which is my best project acronym ever. And this stands for Structural Analysis of Large Amounts of Music Information. Okay. So this is one of 8 projects funded under a scheme which you may have come across called the Digging into Data Challenge. These are really interesting projects. They're international. The funders for this particular one are NSF and SHERC in Canada and JISC in the UK. The whole Digging into Data Challenge was the creation of a guy called Brett Bobley at the National Endowment for Humanities in Washington. And it's, I think, a very impressive program because they managed to get 3 different countries and at least three different peer review systems together. So tremendous interest in the program, 8 projects funded, and this is one of them. We're hoping there'll be a second round of the program. This particular collaboration has all sorts of people in it. So there's myself, Stephen, and Itch as the sort of PIs. NCSA have donated 250,000 nominal supercomputing hours. I'll be telling you more about some of these things as we go. We have various collaborators providing music collections, in particular the Internet Archive. One of the things I've been doing whilst here in San Francisco is visiting there. We have a bunch of algorithms I'll talk about. We have a music ontology from a guy called Yves Raymond, who used to be at Queen Mary in the UK and is now at the BBC. We have various musicologists, including, I share one with MC. And we're building on a framework from an existing larger collaboration called the Network Environment for Music Analysis. And that's very useful because that enables us to do some prototyping, which I'll show you at the end. And finally, of course, the community is very important to this as well. So those are all the stakeholders in this. And this is the big picture. We're starting with some significant digital music collections, in particular the Internet Archive. And I'll show you some data about how much they have in a second. And what's different about this is an exercise in musicology, or in supporting musicology, is that is the scale. So the fact that we have all this digital audio online now means we can do things we couldn't do before. We have come across 1 or 2 musicologists who are alarmed that we might suggest that you could do more than one analysis at once, or multiple people could be involved in one analysis. I mean, this is a real change of thinking in musicology, but it's a big crunch, basically, of the data that's out there, so we can do new kinds of studies. To do that, we need to know the right answers for the analysis of some of this music. So we have a crowdsourced part where we're getting music students in Canada and the UK. I'll show you some of that in a second. And then we do the big crunch, where we take a body of software maintained by the community and use this to do the big analysis on the supercomputer. And then finally, we make everything available to the community because the project will finish after something like 15 months, but we want the activities to be able to be sustained. So that's the big picture. And what I'm going to do in the talk is show you some bits of that, show you what we've already done, and then at the end, show you the sort of use case we're using to try things out and motivate things. And if you want to, you can actually go away and play with the demo, but I won't do a demo today. So the first bit is the collections and the ground truth. So the Internet Archive in particular, you might not think of it as a music repository, because it's familiar basically from the Wayback Machine and people looking at their old web pages. But actually, there are 83,803 live performances in there of concerts. Okay, all sorts of interesting stuff, as you can see. And that's a tremendous resource because in a way, the fact they've also got some LPs digitized isn't so interesting because we have those elsewhere in CD collections, and we might have the musical scores for those that we could analyze anyway. What's interesting is the fact these are live performances. And entirely gratuitously, I now have a picture of a live performance because this is this is Chick Corea and Christian McBride, who played in Yosh's in Oakland last night, and they were fantastic. So that's just to demonstrate this kind of music we want to analyze. Yes. It was an amazing gig. Yeah, there you go. Right. So then we need to know the right answers, if there is such a thing as a right answer, as to what the analysis of this music is. And what we're focusing on in this talk, I'll talk about genre recognition, I'll talk about, in this case, it's chords actually, but mainly it's structure. We know we can extract all sorts of features from music, and we'll do that anyway, and that's okay. The more research question in this is whether we can do structural analysis, and whether the scale of what we're doing enables us to do a better structural analysis. That's the really interesting research question that underlies this. So we've crowdsourced, it's sort of controlled crowdsourced, because the crowd have to be music students at the moment. It's an interesting separate debate as to whether we can crowdsource this to the masses. I actually really do want to do that, because I'm not sure who has the authority on the notion of genre. But so one of the collections we're working, in fact the Southampton end of this, is using the entire US Billboard collection, which is quite fun. That sounds like it's a lot of music. It isn't actually so much, because if you think about it, things are in the charts for quite a while, and there's about 1/10 as much volume of data there as you'd first expect. So we're nearing completion on getting students to do the annotation of this, and the way they do it is they sign up using this website. They get paid money. In the UK, they get paid £4 for doing this. They use a tool which is produced by Queen Mary, University of London, called Sonic Visualizer, which is a great tool if you haven't used it, and it generates RDF, for those of you who like RDF. And with this, they annotate the music, and we're actually, and this is a really interesting, fascinating study in its own right, and I could talk about it for the rest of the day. We haven't mandated how they do the analysis very much, right? It's quite free form, because if we overdo it, they're going to get a particular kind of analysis because of the framework we impose, and that might not be what we can extract with the computer analysis. So we actually want a richer analysis here that itself becomes an interesting study. So for example, here's the annotation of a piece of popular music. Perhaps I should go over to the other screen sometimes, sorry. And you can see that at one level, you get what you expect here. Intro, verse, chorus, verse, chorus, verse, chorus, chorus, outro, silence, end. Okay, and sometimes there'll be a bridge in there. But what they're actually annotating with is sort of saying which segments of the music sound similar. And they're using any letters of the alphabet they wish. So when you see a repetition of little b there, that's something that sounds similar. And then musicians in the audience will recognize this convention. The prime, the dash on those, is the music student saying, this is exactly like that, but slightly different. And it's a matter of debate at the moment as to whether we treat that as a separate symbol or the same symbol. But that's the sort of interesting study we could do out of this. It's a fantastic resource. And by Christmas, that will be complete. There's a lot there already. So we should be writing papers about that. It's amazing.
Why the capital letter?
You know, as I was presenting this, then I was asking myself the same question. Okay. There is a semantics to the uppercase. I'll have to check and see what it is. I think that it isn't that that's just what this particular person did. I think we did actually have something that indicates that. We do have, yeah, it could be. And yes, that's a sort of, the AUB type form. But when they're doing the annotation, it automatically, there's an autocomplete that gives them the tags they've used already. So that encourages repeat use of the same tags. But only for that person, not across the community. There's just so much we could do with this. It's fantastic. Right. So then we have the big crunch over on the right-hand side here. Now, the software that's extracting the algorithms is a great story in itself. Some of you may have come across this. There's an annual, quotes, competition. It's not a competition. It's an evaluation, because it's really not a competition, except, of course, it's a competition, and that's why everyone plays. It's started in 2005. A set of tasks, which are music feature extraction tasks, are voted for democratically by the community. Everyone goes away, improves their algorithms, so they go 1% better, or 0.1% better, or faster, higher quality results. And they submit this, and then at the International Society of Music Information Research annual conference, got the acronym right, which was in Utrecht this year, for example, there's a session where all the results are presented, and we see how everyone's done. It's a fantastic thing. It's like Trek in text. It brings together signal processing people and mathematicians and digital librarians and computer scientists. They're all there. It's so multidisciplinary. It works so well. All striving to make their algorithms go a bit better. So we've got this fantastic sustained body of code which we can throw at all this fantastic data in the Internet Archive. It's kind of nice, isn't it? It's nice when that happens. These were this year's tasks to give you a feel for this. And one of the interesting trends over the years is that it's really gone towards working from the digital audio, where it says audio here, as opposed to coming off the musical scores, which are the symbolic ones. I think my own background was in symbolic, but it's all gone digital audio now. And some of these you'll recognise. McCreary by Humming is a famous one, and otherwise known as sort of melodic pitch contours in the trade. And you've got the genre recognition and so on. And we can throw the code in and we can do these things so we know we're going to do an analysis. The interesting thing is, based on the results of that, whether we can then do something to determine structure. And I can go over this way now. That will confuse the camera. This is an autocorrelation plot. So, I mean, some of you might be familiar with these from other disciplines entirely. So what we're doing is just looking at the self-similarity here, sliding a piece of music, or the features extracted from a piece of music against themselves. And when you get good at these, you can start understanding the structure. If you look along the diagonal here, you're seeing the intro, chorus, bridge, verse, chorus, and outro. It's taken me a while to be able to read these, and doing that by computer is something else. There's some really interesting things you can do in terms of analysing this image to help you determine the structure. So that's one of the emerging techniques which we'll be using. So the whole thing about Murex is it isn't just giving us a body of code. It's got all that social infrastructure as well, because there's the annual competition, there's all the people getting together, there's the support for that. So this is called the Murex Do-It-Yourself web service, where people run their code remotely. And you can see this is a 2007 one. This has been running for a while. So that's a tremendous resource, and we can use that community resource as well in terms of trying things out. So next year there'll be a music structure challenge to try to get the community to engage with what we're doing, and this is one of the ways of bringing the community in. Then the bit at the bottom is our intention from the outset that we are publishing what we're doing as linked data so the community can reuse it as easily as possible. And we're doing this, so here's the linked data cloud. Let's zoom in a bit. And you can see there's a bunch of music stuff here already, BBC Music, Last FM, I can't read it so close, Jamendo, Music Brains. So we're adding to that cloud, and the way we're going to be publishing it is according to a particular ontology developed by Yves Raymond, who's at the BBC now, called the Music Ontology, and you can find out more about that from musicontology.com. So we'll actually be using that. We're doing some other things as well, but we're developing the way of publishing really two resources. The ground truth resource is one, and then what the computers come up with is the other. And this picture turns out to be quite important and interestingly controversial. So we refer to all that digital audio that's out there already as the signal. And it really is a signal in a traditional engineering sense. You'll hear medics and bioinformaticians and historians and others talking about signal as well, because it's great. It's the data about the real world. So there's our signal. Then we create these linked data resources like the ground truth repository and the structural analysis, which is really just metadata pointing into the signal. So we're not copying all the audio files. That's really important. We can't copy all the audio files for copyright reasons. So we're pointing at those. We do these. We publish the linked data. The community uses that. That's what the project will do. And then the controversial bit is we intend that the project will sustain because people will add more signal and the community will create more linked data resources which annotate the signal, and it will grow like that. This slide I used in a keynote at Open Repositories 2010, as you can see. And if you watch the tweets from my keynote, you'll see that this really distressed the repositories community because it's like a web. And what they wanted me to say was, add all this stuff in the green and yellow, we're going to the big blue bit and be maintained. And it's an interesting point. There are two different mindsets there. Is it a web or these repositories? And they're probably both. And that's a debate we could have. And in the context of this event, of course, we have been discussing the use of Zentity for some of those repositories. So that's an interesting issue to put on the table. So I've described something where we've done the ground truth and we're about to do the big crunch. I've been at the archive this week working out how to transfer 11 terabytes of data to NCSA. Which the answer is FedEx. But all this is built on this previous infrastructure that we put together, which has enabled us, therefore, to let's turn my network off, It's enabled us to play and actually have a look at a use case and work with our users to get some understanding of the requirements. Now, this is slightly tongue-in-cheek, as you'll see, but it makes a few points. So our deep research question that we want to ask is, how much country music comes from my country? And you can see what I'm doing here from a linked data viewpoint. I'm bringing in the geographical linked data information with the genres, the classifiers, and so on. So that particular picture suggests a particular country and country music, I think. So this is where we lift the hood and show you what's going on behind the scenes a little bit. We're using a workflow system. We're using Meander, which is developed by the CESAR project, funded by the Mellon Foundation, developed at Urbana-Champaign, and really aimed at a digital humanities community. Now, those of you who know my other work know that I work with other workflow systems. And I'm not one of these people who believes in one workflow system for everything. I think they are all in their niches for good reasons. They've co-evolved with their users. And this is the one for music information retrieval. So we're very happy to be using Meander. It's now actually in version 2. Very interesting developments there. Use of Scala for the execution environment. That's another talk. We're also using this thing, which has come up once or twice in talks this week so far, which is a community website for sharing workflows in various systems, including Meander. And this is something that we've been running since 2007. It's now led from Oxford, because I've moved to Oxford, as we heard earlier. And it's sort of, depending on who I'm talking to, I'll describe it in different ways. It's like, it's Facebook for scientists, maybe, except that puts scientists off, because they think that means everything's shared, and that's bad. If it's a repository, it's interesting because it's a repository of methods rather than data, which we think is very important, because we think there's too much obsession with data, or at least not enough obsession with methods. It's a social network of people and things. It's an interesting way to see how communities share stuff. It's an open source app if you want to do your own. It has programmatic interfaces, and the fact that it's linked data compliant is what's most relevant here. And various other e-laboratories projects have come out of it. So in my experiment, I share these workflows, and this yellow strip that you see down the middle is one of the distinctives. This is what we call the social metadata. It's the credit attribution, licensing, and all those things that and that make scientists and researchers happy to use it, but also fits in with the scholarly knowledge life cycle and the reward structures and the incentives that we have, which is in a sense what this is all about. So that's part of what we're doing. Now, my experiment is linked data compliant. It isn't on the linked data diagram we saw earlier. I don't know why. And when I go to the International Semantic Web Conference in a few weeks, I will try to find out. I'm not sure which bit of social compliance I failed, but we actually achieve every piece of technical compliance that you need to get onto the diagram. I must have linked into the wrong stuff. So this is a sort of arbitrary choice of a semantic web browser just to demonstrate a point. I don't necessarily believe that people should ever see this kind of semantic web interface. It's very useful as a kind of multimeter for engineers to probe and see what's going on. Now I'll come on to that. So I so don't believe in this as an interface that I generally wouldn't show an audience this slide, but it makes the point that, especially here, that the collections of stuff on my experiment aren't just individual workflows, but they're workflows with input and output data and other associated things, which are bundled together in these aggregations using object reuse and exchange. And it all links out into other repositories and so on. So this is working really well, because until we went linked data compliant, if I wanted to integrate my experiment with some repository like ePrints in Southampton or eScholar in Manchester, I had to have meetings and write code. And now it just works. Okay, that's the wonder. We've enabled the join. When people are linked data compliant, these things are a lot easier. There's also a usability cost to the linked data compliance, but that's another talk, which is quite interesting. So, back to the research question, how country is my country? Here we bring together some resources. We've got Gemendo, GeoNames up the top there. I won't do the demo. If you want this demoed, what happens is that you build a collection over that. These are the pointers into the signal. You can publish that for other people to reuse. You then choose, in my experiment, a workflow, a Meander workflow that you want to run. You execute it. It does the classification. In this case, we're doing genre classifications. Actually, it's great. If you can write Sparkle, you can do stuff like this. It's really easy to ask all sorts of questions, but we don't expect our users to do that. Instead, this is why I need to be talking to MC, we have bespoke user interfaces to meet the needs of particular groups of users with particular questions. So this is actually a a typical sequence. And from a sort of research lifecycle viewpoint, this is familiar. I mean, discover, acquire, do some processing, get some results, share, publish is a normal sort of cycle. I'd like to challenge normal cycles, but that's a normal cycle. So in this one, you collect the resources you want together. That's the pointers into the signal. And actually, this is immediately available as a URI. We're very much in the linked data world. You can share that. You can use other people's. We have this notion of grounding, where we actually get the audio files so that we can then do the actual, run the classifiers over it. And that's done by choosing a workflow in my experiment. And then the results. And this is part of the interaction with the results, where here you're seeing a pie chart. This is a rather odd example. If I'd actually artificially done an example, I would have chosen some US music, perhaps. But because everything's published as linked data, you can use other people's collections. So I've used someone's collection, which was to do with German dance. There we go. Which doesn't have that much country music in it, it turns out. But there we go. If you wanted to play with that demo, there's a site, nema.ecs.something.sk/country, where you can step through those things and try it for yourself and make your own selections of music and do the classifications. To close, tying back to Malcolm Atkinson's talk yesterday, this is kind of one of those datascope things. This is a telescope to enable us to look more carefully at the music data and reevaluate our position in the universe. I'm not totally comfortable with the datascope analogy because it's a piece of kit. I mean, it's a piece of kit that's evolved, and new technology causes new, better bits of kit. But I think a lot of this is about people as well. And my preferred sort of slogan is what we're doing here is going from the signal to the understanding. And that, in the context of this session, is very important. We've seen it in the previous talk as well, because that's what a lot of digital humanities research is about. That's very much like a scientific process. That's why there is some sharing of eScience methodology and tooling across the digital humanities. But whether you're working with ancient papyrus, whether you're working with digital audio recordings, whether you're working with various kinds of images, there is a commonality in that workflow, but it's a flow that involves experts as well as equipment. It's something which is an interesting subject of study in itself. My other reflective thought is that I've crossed the line. I have spent 10 years building tools for people in other disciplines, in chemistry, in bioinformatics, in environmental science, in social statistics. And I would never dream of doing the research. I'm just supporting the people who know how to do the research. But in this case, there's a bunch of computer scientists involved who are really engaged with the research problems in musicology. And it's interesting to wonder why that is. And sort of a first guess is that music representation is very rich. But at the one end, you have this beautiful, elegant, symbolic score representation, which is a hierarchy. And at the other end, you've got this linear, dirty sequence of samples. And we're really good at computer science in going between hierarchies and linear things. So that's a suggestion for a possible bar conversation. But I'm really enjoying it because I'm applying computational thinking within the musicology domain. So the take-home message is, this is kind of embarrassingly unsophisticated because it's think of the biggest source of music data we can and the biggest source of compute power we can and all the code we can and just throw it all together and do something. And actually, I must confess that when we dreamt up the proposal at 5:30 a.m. in a bar in Tokyo, that was roughly how the discussion went. But what you're seeing in its implementation is what I would regard as a set of characteristics of eScience in 2010, what I actually call third-generation eScience. So we've got the crowdsourced piece in there. We're always publishing. In the old days, people would warehouse. They'd bring all the data into one place and process it. Here, we're always pushing it out. We have community sustainability built in from the outset. We are doing computational thinking. We're building a generic infrastructure to build very bespoke user interfaces for specific groups of users. And it's massively interdisciplinary. So thank you very much. Those are all the people involved, and that's how to contact me. Thanks.